This video is our first video on concentration. It's going to be a whole series of videos on concentration. Now, concentration is used when describing mixtures, especially referring to solutions. And concentration is just a measure of the solute to solution ratio. There's a number of ways of measuring it, but let's look at what we mean by concentration. First of all, if you've ever got a solution, you've got a certain solute dissolved in a solvent. And concentration is just a measure of the solute to solvent ratio. And so in this sample, if we've got A units of solute and B volumes of solvent, the concentration will be related to this ratio A to B, the solute to solvent ratio. Now you can change concentrations. So for example, if we then added some solvent to this mixture, so we're adding X volumes of solvent, we now have the original volume, which is B, plus X more volumes of solvent. We haven't changed the solute though, the units of solute are still A. So by adding some solvent, what we say is we've diluted the concentration, which is another way of saying decrease the concentration. And that's because in this sample, the concentration is related to the ratio A units of solute divided by B plus X volumes of solvent, which is smaller than this original concentration. Now another way of reducing the concentration or diluting is you can remove solute. If I took out some of these solute atoms from this mixture up here, that would also reduce the concentration or dilute the mixture. But usually when we say dilution, we mean adding some solvent. So adding solvent decreases the concentration or dilutes the mixture. However, you could add some solute to the mix. In this case, I'm adding Y units of solute, but I've still got B volumes of solvent. And adding solute increases the concentration. So in this sample, the concentration is related to this ratio, which is A plus Y units of solute divided by B volumes of solvent. That's obviously a higher concentration than this one up here because the ratio is bigger, and that's the way you usually increase concentration. Usually you increase concentration by adding more solute, but you could also remove solvent to increase concentration. So for example, you could heat this up and boil off some of the solvent, and therefore the concentration would go up. Let's go back to looking at the different ways of actually measuring concentration, the useful ways, and each of these methods is useful in a different way. First of all, you've got volume to volume percent, and that's particularly useful if you've got solutions of two liquids you mix together. To find the volume to volume percent, it's just the volume of solute divided by the total volume of solution times by 100. The next one's weight percent. We use this a lot in chemistry. It's the mass of the solute divided by the mass of the whole solution times 100. And you want to think about it this way. This can be thought of as parts per 100, which will be useful when we look at something called parts per million. Look at the parts per million formula, or ppm formula. It's just mass of solute divided by mass of solution, which is exactly the same as this weight percent, except you're timesing by a million. So parts per million is just like percent, except that in percent you times by 100, in parts per million you times by a million. That's used when the concentrations are very small. But if you've got really small concentrations, you use parts per billion. Once again, it's just the mass of solute divided by the mass of solution, this time times a billion, looking at very small concentrations indeed. But for these formulas, you'll notice that you can use any particular units you like. Usually in chemistry we use grams and litres all the time, and I'd encourage you to use grams and litres all the time. But because these are ratio formulas, you can actually use any units you like. Only catch is, you've got to make sure both your volumes or both your masses have the same unit. So if you choose to use kilograms for your solute, you have to use kilograms for your solution. If you choose litres for your solute, you've got to choose litres for your solution. So as long as you keep the units the same, all these numbers will turn out the same. But perhaps the most useful concept of concentration for chemistry is this concept of molarity, which is moles of solute per volume of solution. And that's usually just called concentration, even though these are all measures of concentration, because this is the most common use of concentration in chemistry. When people just say concentration, they mean molarity. The way to calculate molarity is just C for concentration equals number of moles divided by the volume, or you can rearrange that to number of moles equals concentration times volume, and that's one of the equations we're going to use a lot in this chemistry course, where C is the concentration or molarity in moles per litre, and that can be written as mole/L, or mole L to the minus 1. N is the number of moles of solute, and V is the volume of solution in litres. So that's got to be in moles, and that has to be in litres. So while these formulas, you could use any units you like as long as they're the same, for this formula, you've got to use moles, you've got to use litres, and your concentration will be in moles per litre. Next thing, converting units. Now, in chemistry or physics and all of science, there's something called the SI system of units, and they've got some certain prefixes. N stands for nano, which means 1/billionth. Mu, which is the Greek letter M for micro. You've got M for milli. If there's no prefix, that means the base unit. Now, technically in chemistry, kilograms is the base unit for mass. We use grams in chemistry as the base unit. K stands for kilo, which is 1,000 times. M stands for mega, which is 1 million times. And G doesn't stand for nano. That should actually stands for giga. Giga means 10 to the 9, or 1 billion times. That probably won't, just pay attention to that. It'll probably change when I change slides, but make sure G is giga. There are more. These are just the ones we need to use in chemistry, but you need to know how to convert between these units. Something that someone figured out last year was a little mnemonic for thinking about this. They've tried to remember the order of these things: giga, mega, kilo, milli, micro, nano. with a gap in the middle for the base unit, and that's going from biggest to smallest. And that's what they said. If you know the Game of Thrones series, they said George Martin kills, dramatic pause, many unsuspecting noblemen. And that was a little mnemonic for remembering how these things work. That might work for you, it might not. So what do we do with these? Well, sometimes we've got to convert between units, because sometimes you might be given something in nanograms, but we know in chemistry we use grams. So you've got to be able to convert from a non-standard unit back to the base unit again. So how you do that is quite simple. You just replace the SI prefix, in this case little n for nano, with its corresponding number. So 45 nanograms is really just saying 45, that little nano stands for 10 to the minus 9. So 45 nanograms is just 45 times 10 to the minus 9 grams, which is the same as 45 times 10 to the minus 9 grams, or if you put it in your calculator, you'll get it in scientific notation, 4.5 by 10 to the minus 8 grams. So if you're converting from a non-standard unit to the base unit, you just replace the symbol with what the symbol means. This next one's a little bit more complicated. If you've got the base unit, for example here litres, and you want to convert it to a different unit, what you've got to do is a little bit different. In this case, what you do is you divide by the number corresponding to the prefix. So over here, we just times by the number corresponding to the prefix. Here we've got to divide by the number corresponding to the prefix. So 450 litres, what we do here is we're changing it to megalitres, so we've got to divide it by a mega. So 450 litres is 450 divided by megalitres, or 0.0045 megalitres, or just 4.5 by 10 to the minus 4 megalitres. The third situation is sometimes you've got to convert between two non-base units. So for this example, you might have to go between, milligrams up to G, which should be gigagrams again, converting between 6.5 milligrams to gigagrams. Step 1, you just basically do step 1, then step 2. So the first thing you do is convert it to the base unit, and then you convert it to the other unit, which is the same as multiplying by the unit you've got, in this case milli, and then dividing by the unit you convert it to, in this case giga. So let's do that. So 6.5 milligrams to gigograms, we times by the unit we've already got, which is milli. So that's times by 10 to the minus 3, but then we divide by the unit we're converting to, which in this case is times 10 to the 9. So that turns out to be that little number there, or just 6.5 by 10 to the minus 12 gigagrams. So 6.5 milligrams is the same as 6.5 by 10 to the minus 12 gigagrams. I don't know whenever you never need to do that, but just in case, that's how you can do converting units. You need to be very comfortable converting units. You need to do it a lot in chemistry. So let's look at some examples to see if we can apply those concentration formulae and also converting units. First of all, calculate the weight percent salt in all these situations. Part A, 120 grams of salt dissolved in 1,500 grams of water. It says weight percent, so all these forms are going to use the weight percent of a substance is the mass of that substance divided by the mass of the mixture times 100, or in this specific case, the weight percent salt is the mass of salt divided by the mass of solution times by 100. So in part A, we've been given the mass of salt, 120 grams. We're given the mass of the solution. Well, are we? Let's see, we've got 120 grams of salt dissolved in 1,500 grams of water. That means the solution, the combination of salt and water, is going to be a bit more than just the 1,500 grams. It's going to be 120 plus 1,500 grams. The solution is actually 1,620 grams. So the weight percent salt in this case is 120 divided by 1,620 times 100, which gives us 7.41, or 7.4 weight percent to two significant figures, because both these have two significant figures. Next part is part B. We've got 55 grams of salt was extracted from 1.95 kilograms of salt water. So the mass of salt is 55 grams. What's the mass of solution? The slight change in wording here makes a big difference. The 55 grams this time came out of the solution, 1.95 grams of salt water. So this was the solution. The original solution did weigh 1.95 kilograms. And so that's 1.95 kilograms. But don't forget, in chemistry, or in these particular formulas, we've got to use the same units for both things. We've already got the mass of salt in grams, so we've got to convert this to grams as well. 1.95 kilograms, just to practice our conversions, even though I know you can do this in your heads, we just replace the K for kilo with what it means, and kilo means 10 to the 3, so 1.95 kilograms is 1.95 by 10 to the 3 grams, which is just 1950 grams. So the weight percent salt is just 55 divided by 1950 times 100, which gives us 2.82, but once again, this is to two significant figures, that's to three significant figures. We always go to the lowest significant figures. This has to be to two significant figures, which is 2.8 weight percent. Last question. 1,200 grams of salt was dissolved in 150 kilolitres of water. So the mass of salt is 1,200 grams, or 1,200 grams. It's pretty straightforward. But we've got to be very careful, because this formula is mass of the salt divided by the mass of solution times 100. We've been given the volume of solution, so we've got to be very careful. So what's the volume of water? Well, the volume of water is 150 kilolitres. Just take that kilo out, that's 150 times 10 to the 3 litres, or 150,000 litres. But even still, litres and grams aren't the same thing, and we've got to get this into a mass as well. So we've got to use the idea that 1 litre of water weighs 1 kilogram. So when they say 150,000 litres of water, they actually mean 150,000 litres of water is 150,000 kilograms. But 150,000 kilograms is not the same as grams either. Let's convert that to grams. We replace the K for kilo with 10 to the 3, so that means 150 kilolitres of water is the same as 150 million grams of water. So the mass of solution, this won't make much difference, it's 1200 grams, we've got to add it on anyway, so the mass of solution will be 150 million, 1,200 grams. So now we can go to the weight percent salt, is the mass of salt divided by the mass of solution times 100 gives us 8 times 10 to the minus 4 weight percent to two significant figures.